Hello, everyone. Thank you for joining this talk. Now, this is a talk about Kubernetes and specifically how to run successful attack simulation exercises. Now, first of all, a few words about myself. I'm a senior security consultant based in the Manchester office, where I'm focusing mostly on threat simulation and, generally speaking, collaborative security exercises. Now, other than DEFCON, where I first gave this talk a few weeks ago, I've presented in a couple more hacker conferences, and I'm clearly a fan of Top Gear. All right, let me start with a number. Big old number, 22 minutes actually. Does anyone have any idea what this is? Kubernetes talk, 22 minutes, no ideas. Close. It takes only 22 minutes for a newly created Kubernetes cluster on the internet to start receiving attacks. So, as with everything else, we could say that it's not a matter of if, it's a matter of when your cluster will be targeted. So how do we get the head start? We need a proactive approach. And this is what this talk is all about. Why you need to run attack simulation exercises against your Kubernetes clusters and how to do so, as informed by our latest research and experience running assessments. In some more detail, we'll talk about the threats posed to a Kubernetes cluster and why threat modeling is essential for the success of any security exercise, not just attack simulations. Then we'll dive headfirst into attack simulation topics in Kubernetes, things like tools, operational planning, and eventually the execution of it. But attack alone is pointless if it doesn't support defense, as my colleague Nick said in the early talk. So we're going to cover some basic Kubernetes detection concepts as well to see things from the perspective of the SOC. But before all that, we have to start with an introduction to Kubernetes. Otherwise, everything else is going to sound like Greek to you. All right, so what is this cluster thing? What is this cluster thing that I've been on about? What is Kubernetes? So Kubernetes is complicated, as you've probably already heard. So a word of caution, this deliberately incomplete analysis, which is going to follow, is going to be a little bit technical. Apologies for that in advance. But on the plus side, if you've never looked inside Kubernetes, here's your free primer. Let's get to it. Now, the Kubernetes cluster then, our system in question, consists of a set of worker machines. We call them nodes. And these nodes, in order to run applications, they run containerized applications, and in order to run these applications, they're managed by the control plane over there on the left, and they need to have a container runtime installed, such as containerd. In previous versions of Kubernetes, that could also be Docker, but not anymore. They also need an agent called the kubelet, and kubelet communicates with the control plane, and specifically the API server, to receive instructions. Now, this component, the API server, it's in the heart of the cluster. It's the front end that all internal and external parties communicate with, and it exposes a REST API for them to do so. So clients can talk to that REST API if they want to interact with Kubernetes, clients like users or services like CI/CD pipelines. And most commonly, humans prefer to use kubectl instead of sending raw HTTP requests to a REST API. Now, when it comes to running applications, the basic building block in Kubernetes is a pod. A pod can consist of one or more containers whose images are pulled from registries, as well as volumes, storage resources. Now, what usually happens in the real world is that workloads aren't actually deployed as individual pods, but as managed collections of pods, like daemon sets or deployments. And beyond pods and deployments, there's a few more types of objects that Kubernetes understands, or resources, such as secrets, services, and so on. And all these resources can then be logically grouped into different namespaces for each different project. You can think of namespaces like tenants in the cloud world. Finally, there's a third layer besides the physical and the logical, that of authorization, with the most common authorization model being RBAC, role-based access control. So RBAC defines the potential entities and allows you to write policies for the permissions that these entities will have against resources. So in the context of RBAC, humans are represented as user objects that can authenticate to the cluster using various mechanisms like MTLS client certificates, Active Directory, IAM roles, you name it. And pods or external services are associated with service accounts, and service accounts authenticate using JWTs, JSON Web Sockets. All right, that was the introduction. Thank you for bearing through this. Easy peasy, I guess. Well, one thing to remember is that in Kubernetes, everything can be replaced. It's something that's built to be extensible. So it is 100% certain that your mileage will vary, and you will have numerous third-party technologies running inside your own cluster. Technologies like the ones tracked in this CNCF landscape, it needs to exist in every Kubernetes slide deck. And these technologies then introduce their own set of risks into the cluster. So in order to tailor any security exercise to your environment with its own intricacies, it's essential you perform some threat modeling first. Threat modeling means answering a few questions like what are the assets I must protect? Where would attacks come from? And why would attackers bother with my Kubernetes cluster in the first place? Let's start with an enumeration of the attack surfaces, and this will also help us understand which levels we must execute in if we want to simulate these attacks. In the most typical scenario, attacks will originate from the container level. That's the code running within your pods. For example, think of a compromised web server, think of a backdoored image that found its way into the cluster somehow. And if that pod is assigned a service account, then the attacker can talk to the control plane, hopefully in a limited security context, unless they manage to break out of it. Because if they break out of the pod, then they're on the underlying node, they're on the host, with potential access to other Kubernetes resources from other namespaces, maybe secrets, that would allow them to elevate their privileges, and even impersonate the kubelet. Who knows? And of course, there's always the threat of attacks from the outside world. Think of scenarios like leaked or stolen credentials, a compromised service, a malicious user, a coerced user, etc., etc., etc. So once they're inside your cluster, what will they move towards? What's the final objective? An obvious answer to this one is, of course, the workloads themselves. If Kubernetes is the underlying platform that your critical workloads are running upon, then it's a way into them. So compromising Kubernetes could result in unauthorized access to the data, potentially sensitive data that these apps may be handling, like proprietary software, as we can see in this slide, software that can be backdoored to maybe achieve a supply chain compromise, or simply stolen. Whoops. But actually, that's not the most common incentive we see. In the age of cryptocurrency, every compute resource makes for an attractive target due to its immediate potential for financial returns. Compute, in and of itself, is therefore something worth protecting. And you'll see in this slide various incidents that have been recorded with this particular objective. Kubernetes clusters are also usually deployed as managed cloud services, or, generally speaking, in cloud infrastructure. So instead of going for the applications, a Kubernetes attacker might be looking for a way into that cloud infrastructure itself. But we've also seen Kubernetes attack techniques across all phases of the intrusion lifecycle, including persistence methods that could enable APT-like surveillance through a long-term infection, and even for defense evasion purposes, as after all, Kubernetes is yet another platform where an intruder can dwell in, a less monitored one, usually, which makes it a great place to hide if you want to evade containment measures. Amazing. So we now know what adversaries are looking for. We know where they'll come from. So let's go ahead and simulate them. Now, there are a few different approaches to go about this. Of course, you can always opt for a stealthy, objective-based exercise, or even better, you can follow a purple team methodology. And I know people define purple teams differently. So let me use this definition given by some small consultancy called SpectreOps. It talks about collaboration between offense and defense with the aim to increase familiarity with TDPs. And for a novel environment like Kubernetes, we similarly decided it's more valuable to opt for a collaborative engagement and try and help the blue team understand attacker behaviors, not vulnerabilities. So at WithSecure specifically, we focus a bit more on detection when we're running purple teams. So when planning one, we do it in one of two ways, depending on what we want to achieve. We could either aim to cover as many TDPs as possible, executing them one after the other in isolation, or we could try and chain a few attacks, similar to how a threat actor would move, to make it as realistic as possible. And even mimic a specific campaign from the ones that we saw in the previous slides. And let's look at these two options in more detail, but in the context of Kubernetes. So for Kubernetes specifically, we found that there aren't as many campaigns documented as there are for, say, AD environments, Active Directory. And as a result, there's not a lot of threat intelligence available. So when incidents do happen in other organizations, not yours, they make for a great opportunity to perform an emulation cycle in your organization and avoid it. So in that case, you probably know already which threat actor you want to emulate. But if you don't, the security researchers over at Wiz maintain this great matrix of cloud threats. It's called the Cloud Threat Landscape. That also covers some Kubernetes incidents. And it aggregates threat intelligence from various sources, like Unit 42, Aqua, Sysdig, CrowdStrike, a lot of very valuable blogs. And that's intelligence that you can analyze and recreate in an attack chain, which you can then execute inside your cluster. And as a way of documenting these different emulation plans that I talked about before, is Jupyter Notebooks. Here's one, for example. We see that later in the demo, and we can see there how it also streamlines the execution of the attack simulation. But for more of a one-off assessment, or if you're looking to build a baseline of your detective capability against all the possible TDPs, then you first need a list of the different TDPs for your platform in question. In 2020, Microsoft released the threat matrix for Kubernetes, and that was the first systematic categorization of Kubernetes techniques observed until then. It seems to be actively maintained. Now, there's also a MITRE ATT&CK matrix for containers, but I'm not going to bother with that because it doesn't really care about the orchestration platform. So it doesn't help with our problem. For more technical instructions on how to execute each TDP, you can look at a project called the Kubenomicon. Shout out to Graham Helton, who created this project. Or you can look at the source code of various vulnerability scanners out there on the internet, like KubeHunter by Aqua. And once you've designed these test cases, one good way of describing them is via a code format. And that allows you to maintain them in a version control system like Git. Now, this is a well-known practice in DevSecOps, attack definitions as code, detections as code. We can apply it here as well. So this way, as your Kubernetes environment evolves, so does your repository of attack test cases. Brilliant. Now, we now have planned everything. We are ready to get our hands dirty. We can start bashing kubectl commands and start this attack simulation exercise, right? Well, that wouldn't scale very easily. So thankfully, there are a few simulation frameworks already out there on the internet that can make our lives a little bit easier. There's Atomic Red Team by Red Canary, there's Stratus Red Team by Datadog, there's Pirates by InGuardians, loved by both testers and threat actors. A bunch of different scanners available. Those, however, also only focus on vulnerabilities. But all of these tools, all of them had some limitations. They didn't perform exactly what we wanted. So we decided to extend our own existing tool and add Kubernetes support for it. Our existing tool was Leonidas, and if you're not familiar with it, no, it's not something that I wrote and named it after myself. That would be just a little bit lame. What made Leonidas attractive for the challenge of Kubernetes attack simulations was some of its core principles, like how it was built with extensibility in mind, and how friendly it was to write new test cases without having to be a developer, as well as the ability to run within your cluster and manage its own resources. I don't want to talk too much about Leonidas simply because it's already out there. It's on GitHub. My colleague Nick Jones wrote the original version, and Alfie, I think. He's still listed as a co-author. And there are many presentations out there talking about it. Trust me, it's pretty cool. We use it in assessments. I will give you, however, a sneak peek of Leonidas for Kubernetes. Now, we designed it as a containerized application running within your cluster and distributed it as a disposable image. We wanted something easy for analysts or threat hunters to write new TDPs, which purple teams will then execute simply by interacting with an API, and all the execution logs to be stored so that they can be shipped to a SIEM if needed, along with all the other cluster telemetry. Alongside this new version of Leonidas, we're also releasing a set of Kubernetes test cases, 17, 20 in total, not only to help you get started writing your own attack definitions, but also to showcase the tool's capabilities, like running kubectl commands, running OS-level commands, and even applying custom YAML manifests to do all sort of simulations that you're interested in doing. But you know, as we said in the beginning, the goal of any attack simulation exercise is to upskill defenders. It's to build a capability. It is therefore necessary, especially for a definitive guide talk, to also talk about defenders and what they should expect, how they can prepare for an attack simulation exercise. So lastly, let's look at how operations teams can apply security monitoring concepts of the traditional SOC into a container orchestration environment. We'll look at things like log sources, detection engineering, and so on and so on. The most important building block of security monitoring is arguably logs. Everyone knows that. If you look at the official Kubernetes documentation for logs, you'll find that there are plenty of log sources available, but no standard architecture for what we call cluster-level logging. This is unfortunately left to the users to implement. Roughly speaking, there are three types of log sources that we should care about. There are logs from your application, logs from your code, which are exposed to container logs and pod logs. You can collect them with simple kubectl logs commands, but the caveat here is that these logs are ephemeral, which means that if the pod terminates, and that happens very frequently, these logs are gone. You also get logs from Kubernetes components, like the API server, the kubelet, the container runtime, and so on. These are also stored on the node, similar to the application logs. The caveat here is that nodes in a production cluster will be disposable, which means that if a VM is replaced, these logs are also gone. So you need to take them out of the host while you can. And finally, we have logs that aren't really native to Kubernetes, but are still of interest for the overall ecosystem. Now, if your cluster is a managed service from a public cloud provider, then that cloud provider solutions, logging and monitoring solutions, are also crucial to monitor. And I'm talking about things like IAM logs or guard duty and so on. And similarly, if you host your own internal image repositories, we found that collecting those logs could help in correlation of certain attacker actions, which are otherwise quite hard to attribute. And that's not even the half of it. If I keep talking, you'll figure out there's a ridiculous amount of logs flowing throughout your cluster. But the good thing is not all of them are useful for detecting attacks. The ones that are those selected in this slide. It's those that answer not so much why something happened, but rather who did what, when, and where from. And these security-relevant log sources map to the execution levels, if you remember from a previous slide, providing us visibility on the container level, on the node level, and the control plane level, the three important levels we simulate attacks from. And alongside those, I've also highlighted the cloud IAM logs. You can see them over there on the left, because as we all know, in the cloud, identity is key, and so on. I want to take a couple of slides to zoom in on the most important log source, the true MVP of Kubernetes attack detection, the audit log. Now, you can consider the audit log as access logs for the API server, simply meaning that if you're interacting with the Kubernetes control plane, you're getting recorded, of course, with some exceptions. The resulting events can be formatted in JSON, as you can see on the right, and they answer the security investigation questions that we raised before. Important thing to mention, these are not enabled by default, despite how important they are. To enable them, you need to define an audit policy and then reconfigure the API server, but you can't always do that. For example, in managed clusters, sometimes this is not even possible. Some events will be very noisy, others will be very important, and you'd want to have extra detail for them. And that's why there are a few different verbosity levels available to set for each different event type. You can easily find a simple policy to get started with, like the one in the bottom of this slide, but it's definitely going to take some tuning to find the perfect mix for your use case. The API server can also be configured to store audit logs locally or send them to a webhook. And both of these ways allow forwarding to a scene. Once you do that, you now have the ability to write alert queries upon these logs, which brings us to our favorite topic, detection engineering. Now, in its simplest form, an alert for suspicious control plane activity could be captured just by the verb and the resource, such as list, secrets. And this behavior can then be defined in a Sigma rule for easier management and distribution. We found that there weren't many Sigma rules. Actually, there weren't any Sigma rules out there that operated on audit logs, on Kubernetes audit logs. So we published a few, and we also introduced the backend pipeline just to have something that is supported by modern SIEMs. But attacks could not only target the control plane. If you remember from a previous slide, they could originate from within the container as well. Luckily, there's a lot of research in this area. Many solutions available like Falco or Tetragon that monitor containers by tapping into the kernel of the underlying node. And they do that using eBPF. And this enables EDR-style analysis of the syscalls, which then allows you to author rules in an easy format for suspicious process command lines, suspicious network activity, and other system-level events. And with this, we're now ready to get into the demo. So in the upcoming video, we'll see how we can simulate a fictitious threat actor who gets access to a cluster and perform some attacks. We'll do that using the tool I mentioned, Leonidas for Kubernetes. And after we run the attack chain, we'll look at Elastic and Falco, a couple of defensive technologies that we've set up, just to see if we have some alerts, how they performed, and so on. All right, let me see how this will work. Let's give it a second. I think it is playing. First step is to confirm connectivity to our cluster. Hopefully you can see the screen. Doesn't seem to move. I'll give it another click and wait a few more seconds. It is playing now. Awesome. So first thing to do from our shell is to confirm we are connected to a cluster. kubectl KL is just an alias for kubectl, so we see the cluster is up and running. We've set up a dashboard as well because we like GUI stuff. It's nice and easy. There's a namespace in there called Dharma Prod, which is our demo environment. Only one deployment in there, and that deployment contains just a bunch of pods. One of them looked a bit sensitive, patient DB, who knows? Next step is to deploy Leonidas into that cluster in order to simulate the attacks. We do that using three commands. We use the generator utility. First step is to generate the Kube API, the Python code, translate the attack test cases to Python code, and then we create the Kubernetes resources for Leonidas, and finally apply them into the cluster. Just drop Leonidas into our namespace. Cool. We see that loading. Soon enough, it's going to be green. And once it is, we now forward the ports. So Leonidas works with a Flask service, and we bring that locally with a kubectl port forward command, just so we can talk with Leonidas, the tool that we've developed. So soon enough, we have a port running in port 5000, and we can interact with Leonidas. We can start hitting attacks just by using this UI, using the Flask UI, hit the tryout button, then hit the execute button, provide arguments there. That's one way to do it. But this is not how we're going to do it. We're going to do it with Jupyter notebooks because it's cool. It's a lot nicer and easier to run. So first we need to start the Jupyter service. Gives us another service listening, port 8888. Visit that. We're going to have a directory in there called threat actors, just to put our fancy emulation playbooks in there. And we have one for a fictitious threat actor called OF815. Gets into the cluster, runs some attacks. Now, let's start running every cell. But before we do that, as I said, we're going to look at our defensive capabilities. So that's Elastic, that's a SIEM. We've already forwarded logs. We've set up forwarding of audit logs. We can see them there. And we've also set up some alerts. These are all active. And these are based on the Sigma rules that we created for our attack test cases. We've also set up Falco to monitor the containers from the node level, from the kernel level, the whole EDR stuff I was talking about. Now, finally, we're ready. Let's start running all of these attacks one after the other, hitting run on every cell. So first, to simulate the initial access, the scenario is leaked credentials, right? A kubeconfig file has been leaked. There's a JWT, there's a service account token in this kubeconfig file. We load it in, instantiate a very simple client, and then we start interacting with control plane in this context of the leaked service account. Typical action that attackers would do is just list their own permissions, see what they can do, basically, within the cluster. They see that they can do some stuff about secrets, some stuff about the pods. So obviously, next step would be to enumerate the pods, see what sort of workloads we have in there. They do see that sensitive stuff, patient DB, and also that critical-looking stuff, HVAC controller, who knows. We also had some access on the secrets, so we go ahead and list them as the attacker, and something that looks like a password for a database, so putting A and B together, we execute just one command in that patient DB pod, providing the password that we found before, just to get it dump and prepare for exfiltrating that fictitious data out of the environment. So lastly, they're going to try and destroy some stuff just to cause some disruption. This is going to fail though because they didn't have the access to do so. They didn't have permissions. And finally, just to wrap it all up, just to wrap up the emulation cycle, we just print the summary of all the TDPs that we executed. Back to Elastic. If we refresh, indeed, we see that the alerts are fired. So one thing works, thankfully. And then if we also see Falco and then just refresh the page, we see that it has raised some alerts about the activity inside the pod as well. So everything's working. Our detections are working, our attacks are working, we're good to go. Right, I got a couple more slides after this demo. Awesome. Now, I want to close with a few key takeaways. So first of all, building Kubernetes detective capability is a journey. And the first step in this journey is to understand the threats posed to your cluster. Once this is done, we saw how the concepts and methods of collaborative attack simulations can be applied to this world as well, in order to build defenses proactively. To this end, we're giving the world a Kubernetes native attack simulation framework, soon to be released on GitHub, a set of test cases to get started alongside this tool, as well as the corresponding Sigma rules to these attacks as building blocks for detections. That's all for me. Thanks so much for your time. Any questions? Take that as a no. Yeah.
So you already worked out the dynamic nature. How do you deal with that? Things which are coming up and down to capture the loss. Is that a challenge?
It is.
150,000. Or
Yeah. If I understand the question correctly, the dynamic nature of Kubernetes is always a challenge when security is the topic. So this is just one way to approach it, but obviously it needs to be on a continuous basis. And I think this is where we focused on while building this tool, to make it reproducible, to make it something that development teams, engineering teams, like DevOps teams can just deploy and run attacks continuously. So as the Kubernetes environment evolves, like as this pods gets spun up and down, as new technologies come in, then these guys can also catch up instead of doing just a point-in-time exercise. Simply because it's very easy, like the fact that it exposes a REST API can also integrate it with build pipelines, CI/CD pipelines. Plan is to add a few more features to aid in this approach, but yeah, it's a moving target.
the from an attacker's perspective, when they do something on a ephemeral bot.
Yeah. Exactly. Yeah. And that's the sort of behaviors though that we try to simulate and then train people how to identify, instead of looking at individual vulnerabilities that might come and go, that might pop up when this technology is integrated. The listing of technologies, for example, is something that we can signature. And whenever someone like pokes around in the cluster, that immediately, deviates from standard interaction of like developers and engineers. So, yeah.
Thanks.
And after what Nick, do you feel like there's an opportunity to use this kind of, like, use Leonidas in a more of a CI/CD pipeline of its own, in the sense of like if there's deviations from known good, even just like log health perspectives, like having that in new clusters being rolled out, or changes in configuration to say like we're worried about these TTPs, we've got them documented YAML files. CI/CD only goes green when we know we've got coverage, we've got detections working, we've got log health.
It should be possible. Like, this is definitely an intended use case. The AWS version supported something like that natively. The plan is to implement something like that for Kubernetes as well. But at the moment, we tried not to overcomplicate stuff. Just drop it in the container, drop it in the cluster. It's a containerized image. It's just an ephemeral thing that you can drop in and out. So leave it there, run some attacks, remove all the artifacts as part of the build step, and should probably be fine. Just to give you a dashboard of like, is there anything new in there? Or is there anything?
I knew nothing about Kubernetes before the start of this. I thought that was really awesome talk.
Me neither. No worries.